All too often we see visions of mothers and children walking long distances to go and get their drinking water, only to find that it's filthy and full of disease. Most of us take for granted that when we open a faucet, we will have safe and clean drinking water. However, this is not the case for over 1 billion people on the planet. That's where engineers come into play. Some of us would see this as an impossible situation. That's where engineers come in. They see opportunity and a challenge to make life better. So here at the University of Houston, Department of Civil and Environmental Engineering, under the direction of Dr. Chellam, they are doing water purification studies. I'm Tammy LaBiche. I am a 10th grade IPC teacher at Galena Park High School. I'm also a participant here at the U of H RET program. Assisting me today is Allison Buchanan, a UT biomedical engineering student who is also participating in the U of H REU program. Today we are doing a demonstration of chemical coagulation for water purification. We will begin with Lake Houston water, which is the source of most of Houston and the surrounding areas' drinking water. We will start with 125 milliliters of that. Then we will add humic acid. What that will do is dirty the water basically so that we can see our contaminants when they begin to coagulate. So as you see, the water has gotten very dirty. We don't yet see the contaminants. And we will use aluminum sulfate, referred to as alum. This is a very strong acid, and it will serve to coagulate the contaminants in the water. So now first we're going to add the aluminum sulfate. And to control pH, we will add sodium hydroxide, 6.25 milliliters, and that will bring us to an optimal pH between 6.4 and 8.3 by neutralizing the acid of the alum that we used. At this time, you have to rapidly agitate the water so that all of the contaminants can come in contact with the aluminum sulfate and begin to coagulate. We will do this for several minutes, and at which time then we will continue to consistently stir so that the surface area can come in contact. And at this point, we have a net negative charge occurring, and as the contaminants begin to coagulate, we will start to see things that are called flocks. This is through the process of flocculation. When the flocculation occurs in chemical coagulation, they will then float to the top. At that time, once we have them at the top, we will then be able to filter it and see the contaminants that have actually come out of the source of our drinking water. As we are stirring, it allows for the contaminants to come in contact with the alum, which will then allow it to coagulate. Once it begins to coagulate, we will also start to see flocks. When the flocks start clumping together, then they will sink, and that is due to a decreasing negative net charge. As we stir and we agitate it rapidly, it allows for the surface area of the contaminants to come in contact with the alum, which will then begin the coagulation process. As we begin to get coagulation, then flocks will form. As the flocks form, this is a process called flocculation. The flocks will then sink to the bottom, and they can then be filtered through a regular coffee filter. Now that we have flocculation, we will take a simple kitchen coffee filter and we will begin to filter the water. And at this point, then we will be able to see the contaminants that were coagulated and caught within the filter. This will demonstrate the process of filtration as well as purification. As you can see, we already have a visual improvement from our water sample to our purification water that we have done with a simple filtration through the coffee filter. That is a visual of what we call turbidity. You can actually see the improvement right away. And we will go on to test pH and turbidity between the two samples to show the improvement that has occurred. As you notice, you can see a visual change in the quality, or what we call the turbidity, of the water. As you can see, we went from a dark water, which appears to have contaminants in it, to a clear, possibly safe drinking water. If you notice from our filter, it shows the dissolved matter, which could be dirt, leaves. It could also be some bacteria and things that would go on to make someone sick that we used. Okay, this was our original water sample that we used, and then this is the result of purification and filtration. Now what we are doing is pouring in the filtration water that resulted from pouring it through the coffee filter, so that we have a before and after comparison. Our before sample is on the left and our after sample is on the right. Now we will run pH and turbidity tests on the before and after samples. Our before sample has a turbidity between 24 and 25. So let's see how that compares to our after sample. As you can see, our after sample has a turbidity of 0, which means most of the organic material has now been filtered out. We will now test the pH of the before sample of our water. Now we will measure the pH of the after sample. As you can see, the pH of the after sample is around 6.7. This shows that we have remained around neutral, or a pH of 7. Okay, this was our original sample, which is what a lot of people drink in the world. However, engineers have found a way to coagulate and filtrate water so that it looks like this. As you can see, we have gotten rid of a lot of the organic materials, and the safe pH has remained. So this is what comes out of the work and engineers making our lives better. The work continues here at U of H in the Department of Civil and Environmental Engineering, and there is ongoing work to show that maybe more efficient and effective is a process called electrocoagulation, and that work continues on under the direction of Dr. Chellam.